Hi everyone, today we're going to cover chapter 2.5, which goes over acids, bases, and pH. This corresponds with your textbook on page 32 and 33 of that book. Now, in this lesson, we're actually going to go over water and what happens when it splits. And the consequences of it splitting is the formation of acids and bases, which we can track through the measurement of pH. And a consequence of that is that can interfere with life. So because we have to check with how the things we're learning interacts with life, we're also going to talk a little bit about buffers as well as acid rain, because that tends to have an effect on living organisms. All right, so just a reminder about water. Water is bonded oxygen and hydrogen atoms that are bonded through covalent bonds, right? They form those covalent bonds because oxygen needs 2 extra electrons to fill its outer shell, and hydrogen needs 1 more electron to fill its outer shell, because remember, it's only got 1 ring, hydrogen, which means in its innermost ring, the maximum electrons it can hold is 2, not 8, so it only needs 1 more. Now, one thing I want to also remind you about is oxygen is far more electronegative than hydrogen, so as a consequence, the electrons are actually more attracted to the oxygen atom than the hydrogen atom overall, so it tends to have a negative dipole because it's got a little bit more share of electrons than the hydrogen atoms. Now, there is something that's a little weird though, because if you notice, hydrogen, if you recall, has 1 electron. When it's not bonded with oxygen, it has 1 electron in its outermost valence electron shell out of the 2 it needs, but it's 50% full, which means actually, because if you remember, a lot of atoms accomplish their perfect valence electron shell by either gaining or losing electrons, so gaining electrons until they're full or losing electrons till that outside shell is empty. Hydrogen, though it more often wants to gain 1 electron through bonds, especially covalent bonds, sometimes what it can do is lose its electron and give it away, and instead it's just a pure proton, hydrogen proton, and that sometimes occurs. Now, why is that important? Well, this atom here with no electrons and 1 proton is known as what we call a hydrogen proton. A hydrogen proton, the presence of it, is actually what is measured when we talk about acids and pH. Now, the reason why this is critical is because sometimes what happens is water will actually split. And what actually occurs is one of the hydrogens, there's 2 of them, but one of them accidentally gives away its electron to the oxygen atom permanently, and now it's a pure hydrogen proton. I'll draw that out in a little bit. So now water splits into what's known as a hydroxide molecule, which has an extra electron that it shouldn't have, and a hydrogen, and it shouldn't say hydrogen molecule, and a hydrogen ion called H+. So oftentimes the symbols are written out like that. Okay, so just a heads up, a hydrogen atom is a neutral hydrogen atom with no charge and its normal amount of electrons, but hydrogen ion actually lost its electron, so it's actually an H+, because it lost 1 of its electrons, so it has no electrons now. And hydroxide ion is actually a molecule that has an extra electron that it shouldn't have. Okay? So, the actual drawing of that is, I can show you in a little bit. So sometimes water may split into ions, but it also can recombine to reform water again. The actual splitting of water is quite rare. It's like 1 out of a million, or 1 out of thousands. It doesn't happen all that often, not all the time. But when it does occur, or if it occurs in such a way where more of 1 ion, like hydrogen ion, or more of hydroxide ion are formed than anticipated, it can have really big impacts on the pH, and thus the impact on the actual molecules inside a cell. So I'm actually going to draw out the ions. So here's what actually happened. This hydrogen guy over here decided, hey, I could have 2 electrons or I can have no electrons. So this guy decides to be a weirdo, because that spontaneous breaking actually is quite rare. So it decides to split off and let go and leave its 2 electrons behind on the oxygen atom. So now this hydrogen, which is now a hydrogen ion because it's missing an electron that it normally has, even though it still has 1 proton, is over here. And then the remaining oxygen atom bonded to the hydrogen atom still has 8 electrons. And because the oxygen atom has 6 protons and the hydrogen atom has 1 proton, but they still have 8 electrons, that's why they have an overall 1 charge, because they have an additional electron that actually they wouldn't normally have, since they should have 7 electrons. But this hydrogen guy left behind its extra electron on the hydroxide ion. So that's the idea of the split and actually what it looks like. But these two ions can very easily recombine to reform water. Now, if you've heard of pH, the pH, when we talk about acids and bases, is actually a measurement of the presence of that additional H plus hydrogen ion and how much and how concentrated it is within a water solution. So concentration is the measurement of the relative amount of a solute, which is dissolved stuff within a liquid, per unit volume of solution. So in the liquid in your body, it's the amount of something that's dissolved in that liquid. So the amount of salt you have dissolved in a jug of water, the solute is salt. The mixture of salt and water is the solution. All right. There are different common units that are used to measure concentration, like molarity, which you'll sometimes see. So sometimes you'll see the concentration is 2m or 4m or percent. I'm not really going to require that you understand what those specific units are or what they mean in terms of calculations, but as long as you know 4 molarity has twice as much concentration of whatever solute it is, like sugar or salt, compared to 2 molarity, then you know what concentration is, as far that it's critical for bio. Now, pH is actually the measurement of the concentration of the H plus ion in terms of the concentration of its molarity. So I'm not really going to go into molarity, just trust me. If there's a really big number or a small number, if there's a really small number compared to a bigger number, then that smaller number has way less H plus or hydrogen ion than the bigger number. That's all you really need to know. Now, when we talk about pH, pH is a scale used to determine the concentration of the hydrogen ion that is found in liquid. Now, the pH scale is actually a 10-fold scale, so each level is 10 times higher than the last level, and it's in reverse order. So actually what it means is the highest concentration of the hydrogen ion is found at pH 0, and then the lowest concentration is at pH 14. So the way it is actually a pH number is the concentration of something to its negative exponent. So pH 14 is to 10 to the negative 14, and pH 1 is 10 to the 1. 10 to the negative 1, which actually amounts to this much, 0.1 molarity, compared to 0.0000001 in terms of molarity for pH 14. So every time you go up 1, it's 10 times more concentrated than the last level. So the difference between pH 4 and pH 2 is 10 times 10. So pH 2 has 100 times higher concentration than pH 4. pH 8 has a 3-fold or 1,000 times less concentrated than pH 5, or 1 to the 1,000th the concentration of pH 5. So that's the idea of each scale. So each time you move up the scale, or not up the scale, sorry, move on the scale towards a smaller number, you're multiplying by 10. That's it. That's what you want to know. And what I do recommend that you do is to copy this chart right here. Pause and copy this right now. There was an error on the original slideshow video, but it should actually say that for bases, the hydroxide concentration is higher than the hydrogen in solution. So this section is incorrect, and it has now been corrected. So please ensure your notes has the correct version of the definition for bases. Okay, so when we talk about acids and bases is actually a relative concentration of the H plus or hydrogen ion. So acids have a really high concentration of hydrogen ion than compared to water. So water is actually neutral, like plain clear water. So what that means is it's got actually an equal number of hydrogen ions and hydroxide ions, right? Because if water splits, there should be an equal amount of hydroxide ions made as hydrogen ions, and that's what is considered neutral. And remember, neutral is plus charges balancing out negative charges, and that's why that's neutral. An acid has far more plus charges, meaning it has a much higher concentration of hydrogen ions compared to hydroxide ions. Higher amounts of plus ions over negative ions. A base is a substance that has a far lower concentration of hydrogen ions than hydroxide ions, so it has a much higher amount of negative charge compared to a positive charge. Okay, so basically acids have more H plus than OH minus, while bases have more OH minus than H plus. All right, and the pH scale, because the higher your H plus concentration is, your hydrogen concentration is, the lower your pH is. That's why pHs below 7 are acids and pHs above 7 are bases. Neutral is 7, which is very odd, but that's actually the concentration in life where the amount of the exact concentration of water, of the H plus in water, which is 10 to the minus 7 for the hydrogen ion, is actually also equal to the exact concentration of hydroxide ion. It's weird, whatever, just go with it. Reminder, the information in the video and audio was correct in the prior few minutes, but again, the slide is incorrect and you want to make sure the definition of the base is accurate with higher concentration of hydroxide than hydrogen in solution. All right, so just a reminder, acids are all about extra hydrogen ion, and bases are all about having additional hydroxide ions. And when bases have additional hydroxide ions, that's the biggest reason why it's able to remove hydrogen ions, because that hydroxide ion can recombine with extra hydrogen ions that you may have accidentally added to a base and reabsorb it by turning it into water. Okay? So any acid is going to result in extra hydrogen. Any base is going to result in extra hydroxide ion. And if you mix a base with a little bit of acid, that hydrogen ion can bond to the hydroxide ion. So that's why bases are known to accept or take in or remove hydrogen ions. So just a reminder for the pH scale, pH 7 is neutral, and when it's neutral, that means your hydrogen ions are equal to your hydroxide ions. pHs less than 7 are acidic, which means there's much more hydrogen ions than hydroxide ions. And the pH range, it can actually be 0 to 6, not just 1 to 6. And pHs over 7, which is up to the maximum of 14, are considered basic. And in this instance, because their hydrogen concentration as measured by pH is so low, it also happens to have a lot more hydroxide ion than hydrogen ions. And the biggest thing here is because pHs are associated with having more plus ion or more negative ion, then what that means is if you are at the non-optimal pH for an organism's molecules or cells or body, that will actually interfere with the molecules that are in that organism and can directly affect life and be harmful if you're at the wrong pH. Okay? So what that does mean, for instance, is your stomach is very protected and it has a very high amount of acid, large amount of H plus ion, which means it has a low pH concentration, which actually means that it can damage food that you put inside of it, protein molecules that you put inside your stomach to digest it. But it does mean that the same contents in your stomach, if you moved it elsewhere and drop the pH in your muscles, for instance, it could also break down your muscles. So pH is very unique to the different environments in your body, and there's an optimum pH for your various cells for how they function and when they want to function. So the regulation of your pH is very critical. Okay, so here are some diagrams of pH just so that you can use them as a reference. This is the biggest one. I recommend drawing it out. The actual formula for pH concentration is this. It's actually a log that's used to calculate pH, but basically all that means is the pH is associated with these concentrations. And again, the bigger your pH number, the actual less concentrated you are. And that's what that log formula actually does. It makes the pH concentration drop as the number gets bigger. And this image gives you kind of some perspective about the comparison of the amount of hydrogen ion compared to regular water. That's right over here. So in this case, pH 0, it has 10 million times the amount of hydrogen ion compared to plain water, which is why things at pH 1 and 0 can be very dangerous if you get it on your skin. It can really just damage and burn your skin. Same thing for pHs on the opposite end, because even though it has a low concentration of hydrogen ion, it has an insanely high concentration of hydroxide ion, and it can be really damaging as well. Here's just a picture so you guys can see the difference between, or the inverse of the hydroxide concentration to the hydrogen ion concentration, how as one gets bigger, the other one gets smaller, and vice versa. And here's just a different scale that I think is very pretty and also gives you some pictures of different everyday examples of acids versus bases. It is in reverse order though, so the acid is down here and the base is up here. Sometimes bases are called alkaline, just a heads up if you don't know why it says alkaline and alkalinity here. That just means base. Alright, so the big thing here is you should know strong versus weak acids, bases. A strong acid just means there's a higher amount of that critical thing, the extra hydrogen ion. And a strong base just means it has a higher amount of the hydroxide ion. And if someone says they have a strong acid, it actually means that they have a lower pH within the acid range. So an acid that has a pH 1 is a much stronger acid than an acid that has a pH 6. And in terms of bases, it's a higher pH will give you a more basic thing. So the higher the number, the stronger the base, and the more OH ions, hydroxide ion it has. So a pH 14 is a much stronger acid than it should say base, not acid. Sorry guys, I'll fix that on the slides. Much stronger base than something with the pH of 8. So because pH is really critical for organisms to live, because those ion concentrations of hydroxide and hydrogen ion have a real potential to be damaging to an organism if it's the wrong concentration. That's why we have buffers. So buffers are unique to the different tissues in your body and in organisms, but those buffers are there to keep the pH stable. So if there's a sudden change in the environment or the food that an organism takes in, the pH should still stay roughly the same. Maybe not exactly the same, but still within a range where life can still happen and all your cells and molecules in your cells are still functioning. And what they do is they absorb those extra ions to prevent them from really messing up your pH, or if your pH goes the opposite way, it can donate extra ions to help make your pH go back to normal. Generally speaking, when we talk about buffers, we really kind of just refer to the hydrogen ions. So buffers will, if your pH goes down, you get too acidic, meaning you have too much H+, then it will suck in the H+. And if your pH goes up, it's base, meaning there's not enough hydrogen ion, then what it'll do is it'll give away hydrogen ions so that your pH goes back down to normal where it should be. So it's basically keeping you from fluctuating. Imagine like you get too cold, someone warms you up, you get too hot, something cools you down, that kind of deal. Just a reminder, most biomolecules like proteins, which do the work in your body, only function properly within an acceptable range for your pH. And the fluids of your cells are all about making sure your pH ranges are consistent, which is why they are buffered and they have these chemical substances that keep it consistent. One of the famous chemical substances is carbonic acid bicarbonate. So carbonic acid bicarbonate are actually different forms of the same type of molecule. And these are actually formed by carbon dioxide. So when you breathe in carbon dioxide and that carbon dioxide enters your blood and meets the water in your blood, it forms carbonic acid. So this is what you breathe in, but this is actually what's in your blood. And depending on the pH of your blood, you'll either have more carbonic acid or you'll start forming more bicarbonate material. So, bicarbonate can potentially remove hydrogen ions from the solution. So any extra acid that comes into your body will combine with bicarbonate, and the bicarbonate will get used up to make carbonic acid in the event that you have too much hydrogen ions. So this will raise your pH and remove acid if you use up your bicarbonate. And if you want to lower your pH and add acid back into your blood because your pH is too high, then what you're going to do is you're going to use your carbonic acid and break it down to release the hydrogen ions that this acid can have. And then instead you'll go this way. So it's kind of weird. You're forming bicarbonate, but what you're actually doing is not forming bicarbonate, but you're using carbonic acid to create acid. So it will lower pH and thus add acid if needed. So this is another formula for that bicarbonate carbonic acid buffer. So it's a little counterintuitive. You'll think, hey, I'm making carbonic acid, so I should be more acidic, but instead you're not making carbonic acid, but you're using bicarbonate in order to become less acidic. And if you're becoming more acidic, you're not making bicarbonate, you are using carbonic acid to be more acidic if your pH is too high. So that's the idea of this buffer system. You're just going back and forth to balance out your pH. And actually, the cell that helps deal and control the pH and the movement of this bicarbonate carbonic acid buffer system is actually your red blood cells. Your blood cells actually do this for you and help drive this change so that your blood is at the right pH, and then all your cells in your blood are happy, and then all the fluids that deal with your blood are happy. So all organisms have some kind of buffer system if, they're living and have some capability of moving around the environment. However, there is sometimes environmental issues that can really impact your body. So sometimes your buffer systems aren't enough if you take in too much acid or too much base, more than you can handle. And that's where acid rain comes in. So acid rain is an environmental ecological issue where the burning of fossil fuels actually create acid in the rain that's precipitating from the clouds. So what actually happens is the burn off from fossil fuels that create sulfuric gases and nitrogenous gases in the air, in the atmosphere, recombines with the water that's condensing in the air, and then it actually drops the pH of the rain and creates acid that goes down into the lakes, soil, and streams. And then when that acid flows into the ecosystem and gets into the organisms in the rivers, lakes, or streams, or ground, then it actually will overwhelm sometimes the organism's ability to buffer and handle the pH, because there's a limit to how well you can cope with your pH shifts. Most people can handle a little bit, but too much is bad. Sort of like you can handle 100-degree weather, but you can't handle 300-degree weather, right? You can handle a little bit hot, but not too hot. So that's the same idea of your buffer systems. It lets you deal with a little bit of acid or base change, but not too much. So acid rain is just way too much, and then the organism's pH just stops being stable, and as a result, it can be really overwhelming and lethal to the organism. So this is what happens in the forest when there's acid rain. And actually, acid rain can also break down material that's not even living, such as rocks and certain kinds of minerals will dissolve in rain as well, in acid rain as well. So just a heads up. All right, so that concludes the lesson, and let's go over the takeaways and key vocabulary. So for the key takeaways, what you really ultimately need to know is that water is capable of splitting into two major ions are really important when we talk about pH and life, and that is hydroxide ions and hydrogen ions. Now, when water splits, it can be reversed, but the ions that are created by water can also be created by other substances like acids and bases, and a higher amount of hydroxide ions or hydrogen ions can have consequences that you may not intend. So pH is a measurement of the hydrogen ion concentration in a solution, and it can be associated with acids, bases, and neutral solutions. However, when we say something is an acid, it typically has a pH below 7, while something that is a base has a pH above 7. And when we talk about measurements of hydrogen concentration, the lower number is the number that's associated with a high concentration of hydrogen ion. A higher number is actually associated with a low concentration of hydrogen ion, and it tends to be an inverse relationship with a hydroxide ion. So if there's a low concentration of hydrogen ion, like in the base, then there's a high concentration of the hydroxide ion. All right, so Anyways, in terms of the concentration of hydrogen and hydroxide ions, biological organisms are sensitive to it, so pH is something that's really critical to keep homeostatically balanced, to use homeostasis on to keep it maintained. So buffers are that method for homeostasis in that they prevent change in pH in the cells and allow the cells to continue to function because that pH is relatively stable. One famous example of the pH being buffered is done through carbonic acid and bicarbonate, which is found in blood and helps maintain blood pH. Now, all organisms need buffering to make sure their pH is balanced. However, one environmental issue that we have to be aware of is acid rain. So acid rain is formed when fossil fuels are burned and the atmospheric pollution of that burn off mixes with the rain in the atmosphere and then results in acid being introduced to ecosystems when that rain goes to Earth. And when that acid is introduced in ecosystems, organisms take it in, and if the acid rain is very strong or there's a large amount of it, it can really overwhelm organisms because those excess hydrogen ions interfere with those organisms' molecules and cells and ability to have them function, and that can really be lethal and be dangerous. All right, so these are the key vocabulary terms that you should be familiar with from this lesson. And then in addition to that, you should be able to apply and identify when these words should be used. And one thing is, as we move on throughout the lessons and in future lessons, you also ought to be ultimately able to understand pH numbers as well and be able to do a little bit of prediction as in the way that we instruct you to in class. One last thing I noticed about when I was rewatching the lesson, hydrogen ions, sometimes I use hydrogen proton instead of the word hydrogen ion, and those things mean the same thing. So hydrogen proton is the same thing as hydrogen ion. So FYI, if you were a little confused by when I said hydrogen proton instead of hydrogen ion at the beginning of the lesson, that's why they're used interchangeably. All right, that concludes the lesson. Bye.